Hello everyone, I'm Danisha Murray and this is DG Makes Math Easy. As you can see on your screen, today we'll be doing a video that was requested by a number of you. And so I hope that this will be substantially beneficial to you all. And if it's your first time here, you can let me know in the comments. If this video is helpful for you when you are done, you can also let me know in the comments. Like the video, also share the link so that your friends can also benefit, because the exam is just a few days away. Also, if you're new here, just go ahead and join the DG Makes Math Easy family, just like you know how to, using that red button below this video. All right, we hit the road. In order to do questions involving circle geometry on the CXC paper, you're gonna need to know circle theorems, all right? And these are some basic properties that we must bear in mind to be able to do the questions that come on the paper. A problem that most students have is that they may know one rule, but by the time they look at the question, there are just so many rules to pick out and so many rules to apply. And so you forget what to do. So let's solidify what these theorems are first, and then we try to combine them to do the questions. All right, so the first one says, the angle subtended by an arc at the center. So I'll just annotate as I go along. The angle subtended by an arc, and we know arc is just a portion of the circumference. And in this case, the portion that we're looking at is right here, A to B. The angle that is subtended by that arc, that angle is formed up here. All right, well, we're gonna look at, let's take it the other way around, then I'll say that. The angle that is subtended by the arc at the center, all right, you can see it goes to O there, is double the angle that is subtended by the same arc at the circumference. Now, that's just a short way of saying everything that's on my screen right now. And let me erase everything and say it the way that I was going to say it earlier. This is a way that some persons are also comfortable with it. The angle that's subtended by an arc at the circumference is half of the angle that's subtended by the same arc, but of course, is formed at the center, all right? So let's be practical now. If this angle formed at the center here is 80 degrees, then it means the one formed at the circumference using that same arc is going to be half of 80. Since 80 is double whatever angle is formed at the circumference, then it means that x would be half of whatever 80 degrees is, all right, which is 40 degrees. Some persons get mixed up and think that the one at the circumference is bigger, but no, you can even see it and just make sense of it. The one formed here is definitely a bigger angle. It opens more than the one formed at the circumference. Number two, the angle in a semicircle or angle subtended by the diameter. Here's the diameter. The angle that is subtended there, and if you notice, it is formed on this arc, AB, the one that was red before I touched it. All right, the angle that's formed on that arc, forms a right angle. All right, once it is formed on the diameter subtended, all right, it touches the circumference here. That angle that's formed at the circumference is going to be 90 degrees. We all know that a right angle is 90 degrees. So note that. By the way, some persons say the angle subtended by a chord, and that is okay because a chord would stretch from A to B just using a straight line. All right, which means that the chord AB and the arc AB would be formed pretty much the same place. So you can still say that this angle was formed on that chord. This angle was formed on that chord. or you can say on the arc, right? So right here, the diameter is actually a chord because it stretches from one point on the circumference to another. So the angle that's formed, subtended by that chord, is actually 90 degrees. Anyway, if at any point I'm moving too slow for you, you just go ahead. If at any point I'm moving too fast for you, you can repeat. Angles in the same segment of a circle and subtended by the same arc are equal. Segment is going to be a problem if you don't know what that is. So if you should run an arc from one end of a circumference to another, you're going to have what is called a minor segment and a major segment, small segment and a big segment. So any chord that you form on a circle is going to create two different segments. So now the rule says angles in the same segment. So if I have this chord AB, no angles are formed in this segment. If you realize there's this major segment over here. And so it says angles formed in the same segment, subtended by the same arc. Good, here we can see them. That one goes touch the circumference and comes back to B, and then goes from A again. The next one touches D and comes back to B. If at any point that happens in the same segment and they're both sitting on the same arc or on the same chord, right? I mean, sure that I say that in the same, or I show that in the same order that I'm saying it. If the angles are formed on either the same arc or on the same chord, see them there? Then they are going to be equal. All right. So in this one, as you can see. All right. So let me look at the first one first. Angle 8 degrees here would have been 80 degrees because they are the same. And let's run over to the other circle where you see that you're not given a chord here. That means you must be able to recognize that it's sitting on this arc. All right. Same thing. So they're going to be equal. Number 4, we're coming down. The opposite angles of a cyclic quadrilateral are supplementary. What's a cyclic quadrilateral? That's a quadrilateral whose vertices, see them here, 1, 2, 3, 4. Quadrilateral has 4 vertices. Those 4 points there are touching points on the circle. So this is not a cyclic quadrilateral because only 3 of the vertices are touching the circumference. All right. So cyclic quadrilateral, a quadrilateral inscribed in a circle. So here we go. And it says any opposite angles in a cyclic quadrilateral are supplementary. Supplementary means they add up to 180 degrees. So A and C here, they're across from each other. They add to give you 180. D and B are opposite. They add to give you 180 as well. And it makes sense because you and I know that the 4 angles should add up to 360. All right. 5, the exterior angle of a cyclic quadrilateral. Here's a cyclic quadrilateral inside. Exterior means outside. So the outside angle, form that D right here, of a cyclic quadrilateral is equal to the interior, that means you must go inside, interior opposite angle. So here we are, the exterior angle is equal to go inside and then go opposite to where D is. All right, those 2 things, those 2 angles are equal. Here's a circle that's turned sideways or all kind of ways. All right, there's a cyclic quadrilateral inside. If right here is 92, you just jump inside and then go opposite. Q is also going to be 92 degrees. All right, if we have X here, that's outside of the cyclic quadrilateral, you jump inside and go opposite. That angle is actually gonna also be the same size as what X should be. So X is 102 degrees. Number 6, a tangent of a circle, and the tangent is a line that touches the circle only once, and that's going to be on an outside point of the circle, clearly. Tangent is perpendicular, so clearly you start thinking 90 degrees, right angle, perpendicular to the radius of the circle at the point of contact. So if you have a radius here, as you can see, and once it touches a tangent at that point, a 90-degree angle has to be formed. If I put another radius here and I draw a tangent to it like that, a 90-degree is formed. All right. Next thing, so number 6 led to the other one. The lengths of two tangents from an external point. So here are the two tangents. From an external point, T. So the two tangents are coming from T to the points of contact on the circle. These two lengths must be equal. So TP and TQ would be equal. All right. And it's kind of obvious. Number 8, we're coming down. This is the penultimate one. The angle between a tangent to a circle. So the tangent here. The angle between a tangent to a circle and a chord. So see the chord here. Let me use a different color. Red. Here's a tangent. Here's the chord. The angle between a tangent to a circle and a chord through the point of contact, that's where they meet. The angle there, this angle is equal to the angle formed in the alternate segment on the same chord. Let's say that again. The angle that is formed between a tangent and a chord, right, is equal to the angle in the alternate segment. So the angle that sits on this chord, and you can turn your screen sideways if you want so that you can see the angle up here, so we sit down on the chord. All right. The angle that's formed from that chord going to the circumference, those two angles are equal. All right. So the one between the chord and the tangent is equal to the one that's formed on the chord but goes to the circumference. And see, it says in the alternate segment. So one segment over here, so the next segment over here, so those two angles are equal. And finally, I think the line joining the center of a circle to the midpoint of a chord is perpendicular to the chord. Have to be. All right. So this is the chord. This is the middle of the chord. If you draw a line from the radius, from the center of the circle, sorry, to the midpoint of that chord, it has to be perpendicular to it. You can put one next chord up here, so, sorry. Find the middle of it, and I draw a line from the center to it that has to form 90 degrees. So that's that, and we go straight to the CXC questions. And just before we begin the actual CXC questions, we are going to look at just a few things that you must know, a few things that's involved in geometry, but not necessarily directly attached to the circles. So it will be plastered all over the circles, these concepts. They will be, you know, all over the circles that you'll be given. So just see how best you can pick them up, just some general rules that you should know. As you can see on the screen, angles in a triangle add up to 180 degrees, and we know that's pretty simple. And also that base angles in an isosceles triangle are equal. So an isosceles triangle is a triangle that has two sides and of course two angles equal. That is so good. All right, so if this is an isosceles triangle, it may be marked with same thing on both sides. So you would know that both of those sides are equal. Now, if both of those sides are equal, then these angles are also equal. All right. they won't always be a base angle per se, because it won't always be the angles that the triangle is sitting on. But whether it's turned sideways, whatever, good. So if we have a triangle like that and these two sides are equal, you know, these two angles here are equal. So just look out for that. It's a very popular concept. First thing you want to do in when you're given these circles, you want to look out for the theorems. Before you even start, just go ahead and observe, right? I'm in the exam and I'm asking myself, what are the different things that I recognize? All right. If this angle here is 20 degrees, then this one is going to be 20 degrees. You'll have the paper in front of you, so you can turn it sideways just to see that this is indeed an isosceles triangle. How do we know that both of these sides are equal? They are both, that's two radii, so we know that they must be equal lengths. So this part can also, would also be 20 degrees. And if we know those two angles, we can easily know the third angle in that triangle, BOE. That triangle right there, we can find the third angle. That's the one formed at the center. And also, if we know that angle, then it's easy for us to find the one here formed at the circumference. They're both on this same chord here, on the chord BE, or the arc BE. And if I know that angle formed at the circumference, I also notice that there's a cyclic quadrilateral. So before you're even asked anything, just observe. If you know that angle formed at D right there, you can easily find this one formed at F. All right, because you know opposite angles in a cyclic quadrilateral, they are supplementary. But anyway, let's see if we pick up anything else quickly. Let me clear the screen. All right, we have an angle between a tangent and chord right here, that's 42 degrees. Angle between tangent and chord, 42 degrees. And we know that if we look at that same chord and the angle formed at the circumference on that chord, we know that they should be equal. So right here should be 42 degrees. And earlier we established that this little part here is 20, which means this is 40, this part would be 22 degrees, the remainder of the 42. But you're looking for stuff like those. And maybe finally, let's look at one last one. Here is a radius and tangent. You already know that this forms 90 degrees. So if you were ever to be asked what's the value of here, this angle here, you know, you could easily subtract 42 from 90. So you make all those observations and you should be well on your way. Here we go now. When you observe, there's nothing you can be asked that you can't answer. What's angle BOE? You go from B to O to E. So that means we're looking at this angle right here. And you and I just looked at the fact that we basically already know how to find that angle there. All right. Importantly, it said calculate giving a reason for each step of your answer. So how do I get to BOE? First of all, I need to know what this part here is. And that angle is BEO. So we need to mention that BEO is 20 degrees. And you add in a reason right there. You write, you say, these angles in an isosceles triangle are equal. Done. And then you put in your 20 on your circle, inside a circle. All right, and then you show now that since you know BEO, you can tell what angle BOE is going to be. And that is going to be the remainder from 180 when we take out both 20 degrees. All right, so we know that all three angles in this triangle add up to 180 degrees. And so that means 20 plus 20, 40. Subtract that from 180 degrees, I will get 140 degrees. Excuse me writing across with the equal signs. I'm not going to have much space. All right, that's it. We know that right here is 140. Angle OED. You take your time and you identify the angle from O to E to D. And already you're bingo, because we had looked at that little part and we said that this part here is 42 degrees that I just highlighted in blue. It's formed between tangent and chord. So all I need to do is look on that same chord, but in the opposite segment of the circle, and up here is going to be 42 degrees. All right, all of what I just put in red. Now, let me get this cleaned up a bit. Good. Now you have to say to the examiner that BED, angle BED is 42 degrees. How do you know that? You write at that point that angle formed between the tangent and the chord is equal to the angle formed in the alternate segment. All right, you show that 42 and then you say, you know then that angle OED is equal to the entire 42 degrees. All of this angle right here that I just placed in navy blue, all right, minus 20 degrees, that is going to give me this remaining portion that they're asking for, which is 22 degrees. And finally, what is angle BFE? Angle BFE, let me clean this up a bit. 22. BFE. Remember our earlier conversation where we said if we know how to find 140 here, we know how to find that angle BDE right there, right? And of course, we definitely know the reason for that. So angle BDE is going to be the angle that's formed at the circumference on the same chord as this angle that was formed at the center. So that's going to be 140 degrees divided by 2, which will give us 70 degrees. You pause, and since you have to give a reason for each step, you say the angle formed at the center of the circumference is, formed at the center of the circle is twice the angle that is formed at the circumference of the circle, extended or subtended by the same arc or chord. All right. And once you know that 70 degrees, then automatically you know you're going to know angle BFE. All right, so you do realize by now that you have to listen to me plus watch me write. I'm not writing in the reasons, but I'm telling you them as we go along. Angle BFE, that's going to be the opposite angle to BDE. So, and we know that these opposite angles in the cyclic quadrilateral, they add up to 180 degrees. So you know you're going to write that as your reason. 180 degrees minus 70 degrees gives us 110 degrees, and we are done. All right, feel free to go over any of these, and I'm going to just run on to the next question. As we go along, it's very important that you note that most of the questions will state that the diagram is not drawn to scale. All right, center O, EH, and EF, those are tangents to the circle, as we can see. Tangents to the circle, EH and EF. FOG, you want to follow when you're reading the question. So you go FOG and JOH, they are straight lines. All right, fine. And the measure of angle FEH is 44 degrees. All right, you start to make some observations. Here is a radius and tangent between that is going to be 90 degrees on that side, 90 on this side as well. we also know that if we're measuring from this external point here, E, to H and to F, this angle and this angle, they are going to be both sides, sorry, EH and EF, they're going to be equal. All right, so you spend a little time and you make some observations. All right, we also know that this angle formed here is going to be 90 degrees, and you may want to spin your device a bit so you can see what I'm talking about. Remember, when an angle is formed on our main chord, the diameter, when an angle is formed at the circumference, that angle is going to be 90 degrees. And of course, we can see another one here. Here's another diameter. Here's an angle formed on it. It's going to be 90 degrees. All right. And of course, we also know that if we have this chord HF, the angle that's formed here at the center is going to be twice the angle that's formed up here. It's on the same chord, but formed at the circumference. Anyway, here we go. And you can pick out the other little rules along the way. All right, here we go. EHF, angle EHF. All right, now we had established when we observed the diagram that this and this, the lines EH and EF, they are equal. And so you can observe an isosceles triangle here for HEF or EHF, which means both of these angles should be equal. All right, and so you go, all right, this one did not, oh, all right, maybe it said reasons along the way, give you reasons along the way. All right, so we are definitely going to talk about the reasons. All right, so here we go, angle EHF. So we did say there's an isosceles triangle, so we're simply going to say to find, in red, EHF is going to be 180 degrees minus 44 degrees. And whatever answer we get, we are going to be dividing it in two because we know that these two angles are going to be equal. All right, so you can stop and work it out first, or you can just simply put a bracket to show that you're going to divide that answer by 2. All right, 180 minus 44 will give us 136. And once you divide that by 2, we will get 68 degrees. All right, so let's just put that in. You want to be using a pencil on this graph, definitely, so that you can rub out what you don't need and stuff like that. You can let whatever you want stay, etc. Okay, and then we have FGH. FGH. All right, bear in mind you can use different methods to arrive at your answer. I'm just going to pick one. So FGH is right here. You may want to recognize the fact that it is formed inside this triangle GHF. All right, and then you want to remember that you're looking for just that part up there. All right, now you and I had already established that right here is going to be 90 degrees. Also, if we look at the third angle in this triangle now, if we notice the line GOF meets the tangent EF. So we should expect that this radius and tangent here, as we said before, meets at 90 degrees. And if we know the part that is 68, then it is easy for us to find this part here. And if we find this part here, then it's easy for us to find the third angle in the triangle. However, we could go simpler. And that will give you 68 degrees. But here we are, watch this. We know that HFE is 68 degrees. And we also know that there is a chord here meeting a tangent. And we should remember that where the tangent and chord means, we should just look at that same chord, but in the opposite segment, in the alternate segment, it will be equal to this angle right here. So it's very straightforward that that angle FGH is going to be 68 degrees. So you could have used the long working that I said earlier if you recognized all of those properties. However, if you just remember the rule that or made your observation from when you just did the question, you would have recognized the angle between tangent and the chord. All right, 68 degrees, and you write your reason. Angle JHE. 68 degrees. All right, so we're at angle JHE. Let's just mark that. JHE, and that should not give you much trouble. That's because if you're in the exam and you just spin your paper nicely, you would have already recognized, especially if you observed at the initial stages, that this radius here and the tangent met here. And again, you might say, but it's not like 90 degrees. Just a second. You would say, but this don't look like 90 degrees. Remember, the diagram is not drawn to scale. So you can go ahead, write your 90 degrees, and then you give your reason straightforward. Wherever the radius and the tangent meet, it's going to create a 90-degree angle, or they're going to be perpendicular to each other. JGH. Clean this up a bit. JGH. And we talked about this when we just start. All right. Let me give you marks, you know. JGH. If we notice, the angle JGH is literally sitting on this chord, and this chord is a diameter. So that's going to be JGH. It's going to be definitely 90 degrees again. And you give your reason. Angle formed at the circumference, but it is subtended by the diameter, is going to be 90 degrees. All right. And so we move to our next question, and very simple, well, very short. It says P, Q, R, and S are 4 points on the circumference of a circle shown below. So already you're thinking, oh, a cyclic quadrilateral. And already you start to think that, oh, I know how to find P, you know? All right. And because of the opposite angles. And then you're also thinking, as soon as you look at the diagram, but wait, if I know this 58, then I can easily know here. All right. And if I know that middle, that angle formed at the center, I can easily know these two because of angles in an isosceles triangle. But anyway, let's continue. It says the angle QRS is 58 degrees. And then it says, using the geometrical properties of a circle to give reasons for each step of your answer. So sometimes it says give reasons. Sometimes it says give reasons for each step. All right, SPQ, so said, so done. So get into the frame of mind easily that you know, you can kind of pick up what they're going to ask before the question is even asked. SPQ is right here. And we know opposite angles in a cyclic quadrilateral, they are supplementary, or you say they add up to 180 degrees. So 180 degrees minus the 58 degrees, that should give you your answer. And then you will also, this was just one step. So this didn't take much. So you just give the one reason. All right. And that one reason is the opposite angles in a cyclic quadrilateral at 180 degrees. OQS. Let me just move this up a bit. OQS. And see, as we talked about it, we knew they were going to try to ask us to find that. OQS. That means we are looking at this angle right here. And as we discussed, if we know this angle formed at the center, it's easy for us to know any of these two side angles. So you show that you know how to find SOQ first. SOQ is going to be 58 degrees times 2. And that's because the angle that's at the center, sitting on the chord QS, is double the one that's at the circumference, sitting on the same chord QS. All right, so we have 116 degrees for right here, which means we know that inside this triangle here, the other two angles should help the 116 to make up to 180. Plus, we know it is an isosceles triangle. Please look out for those isosceles triangles. So it's going to be OQS, angle OQS is equal to 180 degrees minus 116 degrees. And whatever that answer is, we are supposed to be dividing by 2. All right. It's going to be, oops. All right. $32 degrees, and that one is finished. All right, we can probably do just one more. It says, diagram shows a circle center O. The line UVW, as we can see, is a tangent to the circle right there. All right, and ZOXW right here is a straight line, and we have UOX being 70 degrees. And already you start to think, oh, that 70 degrees angle is formed on this chord. So automatically, the one formed at the center is going to be half of the 70. At the circumference, sorry. The one here formed at the circumference at the point Z is going to be half the 70. You look out for those. Those are the very, very simple ones. Well, all of them are simple. Right? You have 70 here. You want to look at these two because that's an isosceles triangle. All right. You also want to look at the fact that this is 90 degrees. This is 90 degrees. You also want to look at the fact that this is a diameter because it goes through the center. And so the angle formed here on that diameter is 90 degrees. The angle formed here as well is 90 degrees. So all of those. So it says calculate showing working where necessary. So you don't have to give reason this time, but you're working. The measure of angle OUZ. OU. Oops. All right, which means we're looking at this angle right here. A bit tricky. Not quite. But anyway, as I said, you just need to know the basics. If this is 70 degrees, if you notice, this is a straight line. And so, if right here is 70 degrees, you're going to look at angle at a point now. The remaining angle right there at O is going to be, it's going to make up to 180 angles on a straight line. All right, so you can say, you know that ZOU, that angle that I just marked in red, is going to be 180 degrees minus 70 degrees, which is 110 degrees. So you're like, oh, if right here is 110, then I can easily find any of these two. And that's what they asked me for. They asked me for OUZ, angle OUZ. This is an isosceles triangle, clearly. So we're going to be taking out 110 from 180. And then divide our answer by 2 so that we can get the angle that we want. 70 degrees divided by 2 is 35 degrees. So that's done. And then we have U, V, Y. So let me put in what we just found. 35 degrees. U, V, Y. We need this angle right here. Again, there are more than one ways. I'm just going to pick one. So we have UVY. If you notice, there is one big triangle here. All right. Using those same letters, UVY. And so if you know this angle here, which is 90 degrees, of course, and if you know this angle here, which you and I just said is going to be 35 degrees. So we're going to show the workings for that. Then we can easily know the one we are asked to find right there. So we show that we know, well, we can say YUV is 90 degrees. We're not asked to give a reason, so you don't have to. And angle UYV, that's the one at the circumference there, is going to be 70 divided by 2 based on the angle we see formed at the center. And then finally, we give them what they asked for, U, V, Y. That's going to be, those are 3 angles in a triangle. So you go ahead and you subtract 90 and 35, subtract that sum from 180 degrees. And that's going to be 180 degrees minus 125 degrees, which should give us 55 degrees. All right, so right here would be 55 degrees. And then we just have one to go. All right, and that one is going to be UWO. Let's just highlight where that is. You just need to follow the letters. UWO. That's going to be right here. Again, pretty easy. If you notice, I'm going to put in green right now. There's a triangle right here. And if you know that this is 90, this one is 70, you can easily know this one. All right, you get the point. And then I'll just tell you off the top of my head that that one is 20 degrees. All right, easy. And then, so you notice that if you just study the theorems then one by one, and then you look at the, just repeat the video if you need to go back. And then you look at the theorems all coming together in like one circle. All right, because that's when people get confused. Now this says name the triangle in the diagram which is congruent to triangle ZOU. And when you think congruent, you just think equal to in terms of you may, all the angles in the triangle are equal, and all the, well, in both triangles, they're going to be equal, and the sides are also going to match in sizes. So the triangle is equal. That's it. All right, ZOU. That's this triangle. Which triangle look like it? Exactly like it. That's going to be this one, YOX. Good. And you think that this is really ridiculous. Is this really what they're asking for? Yep. And the next one is YXU. YXU, this triangle. Which triangle is congruent to it? That's going to be this one, ZXU. That's it. And I think I'll stop here for today. I think you get the point. All right. Here are some other questions I'm going to put on the screen that you can try on your own. All right. Just about 2 more. I'm just going to leave it on the screen for a while. And that should be it. Do not approach the circles as if they are hard. Just know the theorems, know them separately. And then when you see a question, go ahead and pick out the theorems that you can pick up. And then you go ahead and attempt the question. All right, and that is where we will stop for today. This video has been promised a long time, finally being released. So
I'll see you in a